I think we are live now. Am I live? Yes, I'm live now. So, hi, Priyanka, good afternoon. So, yes, we were to, yeah, in today's class, we'll be discussing about meter grids, then potentiometer. So, these are the applications of the things which we have studied so far. So, once this is done, guys, we are good to go with the tests. Okay. Okay. So yeah, let's get start with preparation. So we can start our preparation for tests, and I don't know if we can have a proper test for you guys, um, because time is also less. Huh? Okay, is my voice audible, guys? So is my okay? Let me know if my voice has any modulation problem. Like, say, what happens? I'm in a closed room, so sometimes there might be an echo, or sometimes my voice might not be audible at all. Right? So after I other situation, if there exists such a situation, please let me know. Okay, at any time. So guys, yeah, with this we have yeah. Hope everyone, yeah, everyone says that my voice is audible and everything is loud and clear, right? So we'll start with our class. So let's start with the revision. Okay. So I'm going to end the poll, guys. Thank you. Yeah, recording on. So hi, Lakshmi, Nikita, Girish, hi, good afternoon. So guys, yes, come on. So what did we study in our previous class? So in our previous class, we started with something called as galvanometer. What is a galvanometer, guys? What is a galvanometer? Please tell me what is a galvanometer. So please make it interactive, guys. So let us add all sorts of things and let's make our class more interesting. More the interaction, more interesting it becomes. So if you don't say, I mean, come on. So galvanometer. Okay. So I have heard this galvanometer. I know this meter. This meter is a good meter, which has a needle and has what has a box. So what is this meter? What does this meter do, guys? Galvanometer. Yes, galvanometer is a device used to measure current. Yes, measure current. So we studied about galvanometer. It's a current sensitive current measuring device which shows the direction of current as well as measures the amount of current. So next we studied some conversions. So galvanometer to ammeter. So what was happening here? So what happened? So when we connected a circuit, so how are we going to measure our current, guys, in series or parallel? Sorry. Okay. Okay. Are we connecting our ammeter in series or are we connecting our ammeter in parallel to any network? So when we are going to measure the current, what is the way we are going to connect our ammeter? One word answer, please. Series, parallel. Series or parallel. Always we measure the current in dash in the blanks. Come on. Fill in the blanks. We measure current in dash. Of course, series. Yes, super, guys. So always we measure current in series. So we connect the ammeter always in series. Okay. So an ammeter is a device. So what is an ammeter then? An ammeter is a device which has a galvanometer fixed with a shunt resistance. So what is shunt resistance? Don't worry, shunt resistance is not a new word. Shunt, which means before the British era, before the Britishers come, we used to call shunt as the parallel. So we used to call parallel as shunt. Okay. So whatever we know today as parallel, in the when they invented ammeter or anything like this, it was called as shunt resistance. Okay. So what was the expression for shunt resistance, guys? S is equals to. I want everyone to answer this. Come on. Yeah. So what is the expression for shunt resistance? Yes, shunt means parallel. Yes. Shunt resistance expression. So how to find the resistance of this shunt resistor? So S is equals to. Come on, guys. I'm waiting for response. I, please, come on, guys. If you don't answer, nani. So Ig by G, sorry, Ig by I minus Ig, right? So S is equals to Ig by I minus Ig, correct? So Ig into G, sorry, Ig into G by I minus Ig. This is the shunt resistance. Okay. Come on, next. What we studied next? Next we studied about voltmeter. What is an voltmeter? Voltmeter is a device which is used to measure the voltage. Always voltage is measured in parallel. Okay, in parallel. Voltage is always voltage is measured in parallel. Always the voltage is measured in parallel. Okay, so it's also called as voltage is measured across any device. Okay. Voltmeter is a device which measures the voltage without tampering the voltage value or without tampering the true value of voltage. So, whenever we connect a galvanometer in series with a high value resistance, a series resistance RS, so whenever we connect a galvanometer with a high value resistance RS, we get the voltmeter. So, what is the value of this series resistance RS connected? So, who will tell this? Come on. Very good, Prajwal. Prajwal had given the previous answer. Very good. Okay, Hari Prasad. So Priyanka Hari Prasad had also given the previous answer for shunt resistance. So yeah, guys, come on. Now give me the value for series resistance. What is the value of series resistance? No. Okay. So it was, yes, exactly, guys. V by Ig minus G. Guys, is there any lag in my voice or lag in my video? Guys, I feel there is some lag in the video or lag in voice, is it? Is there any lag in voice or video, guys? Please let me know if there is any. Okay. Okay. So yes, this is the series resistance which is used to convert the galvanometer into voltmeter. Okay. So RS is equal to V by Ig minus G. Okay. This is the value. So if anyone missed, please recall here. Okay. Next, we studied about something called as this. What is this? Godi bridge. Okay, we call it as Godi in Kannada. So it's Godi's bridge. Godi Kallu bridge. It's called as Wheatstone bridge. So Kallu means stone and Godi means wheat. So we call it as okay. Never mind. So Wheatstone's bridge. What is Wheatstone's bridge? What is a Wheatstone's bridge? A Wheatstone bridge is a device which is used for identifying, or it is used to find the value of unknown resistance, right? Of unknown resistance. So the Wheatstone bridge circuits look something like this. So I have a resistor, one more resistor, third resistor. Yeah, I have 4 resistors. Say if A, B, C, D is the arm, then I connect a cell across A and C, and current flows from here I. So I'll connect a galvanometer here, guys. Okay, this is my connection. So what happens? I have so how I said it was, yeah, we have R1, R2, R3, and R4. Okay, here my R4 is unknown. Here my R4 is unknown. R3 is variable resistance. Okay, R3 is variable resistance and R4 is unknown value. Okay, this is what. Now I have to adjust my R3 such a way that the current I1 will be equals to I4. And sorry, no. The current I1 and I2. So I should make such a way that I1 will be equals to I3 and I2 is equals to I4. Okay. then I'll get an expression. Yes, correct, Prajwal. Super, awesome, you go. Hari Prasad, super, Ramakrishna Reddy, awesome. Nice guys, cool, cool, cool. So if we take the ratio, then we can take the ratio of resistance R1 by R2 is equals to R3 upon R4. Sorry, R4 upon R3, right? R4 upon R3 or R3? Okay, R3 upon R3. I think it's R4 upon R3. Yes. So even rearrange, if I try to rearrange, what will I get? R4 is equals to R3 times R2 by R1. Okay. Don't know, guys. There is some lag. Okay. So whatever I'm writing and whatever it's appearing, it's taking some time to show up. So yeah. Okay, this was what we had studied in our previous class, guys. So I hope everyone remembers all of it. Please give an yes if you remember all of this, whatever we discussed. Guys, any doubts in any of these? Any doubts in this? Okay, so in today's class, no doubts. Good. In today's class, we'll be starting with something called as meter bridge. So a meter bridge, yes, we'll be starting something called as meter bridge. It's nothing but the application of galvanometer. So a meter bridge, let's quickly start this. So the definition for meter bridge is given as a meter bridge is an instrument that works under the principle of Wheatstone's bridge, used to find the value of unknown resistance of a conductor. So what happens? Say if we have a conductor, we have to find its value of resistance. So I don't know how to apply. So what we did, so there was this guy Wheatstone. The Wheatstone bridge, this guy Wheatstone gave this method, right? Wheatstone's bridge. So that practically when we apply, we get a meter bridge. So how does a meter bridge look? Have you seen that, guys? Meter bridge? If you had been in school, you would have seen by now. Okay. If you had been in school, you would have done this experiment also. But by now, maybe you might have conducted this experiment in OLabs. In Takala Bantapa, OLabs. So yes, this is how a meter. Okay, let's study about the construction. So how does a meter bridge look like? Okay, in a meter bridge, we'll be having. So there will be a bridge. Okay, so this is nothing but. So there will be a there will be an unknown resistance. So what is this? This is an unknown value of resistance. Now this resistance is compared with the standard value of resistance. So whatever the unknown conductor, say if I have an conductor, I don't know its resistance. I don't have a multimeter, I don't have an ohm meter, nothing like that. So what I do, I'll connect that resistance in this across this 2 points. So in the left half of the arm, say I'll call this A and B. So this A is nothing but same A. So across A and B, I connect this unknown resistance. Across B and C, I connect the standard resistance. Okay. And from B to G, so from B to D, there exists a galvanometer. So galvanometer, you all know, it measures the direction of the current and also the amount of current flowing through it. Now, there exists a 100 centimeter wire. So that is nothing but 1 meter wire. Okay, have 1 meter wire, 1 meter long wire. Now, what is the use of this wire? This wire is such a wire that it does not change its resistance, or its resistivity is not going to change with temperature, right? So this wire, which is connected between across A and C, this wire which is connected between A and C is the wire made up of a material whose resistance remains constant and doesn't vary with temperature. So here I have some notifications like R, where R is the resistance of an unknown conductor. S is the standard resistance. Say you might have known it as a standard resistance box by now. So there is something called as resistance box. With that resistance box will give a standard resistance. Okay. But today, though we have the latest, so in our previous class we studied about carbon resistors and all, right? So though we have carbon resistors, they are bound to have certain errors. Okay, that's why while doing the experiment, guys, so there was some error in carbon resistance. You remember? Do you remember there was some error in carbon resistors? So gold had 5% error, silver had 10% error, and no color had 20% error, right? So to avoid that error, what do we do? Always in our experiments, in our labs, we use a standard resistance box. So there is a resistance box. So this resistance box is said to have negligible error. Okay, even it also has some errors, but it's negligible than that of the carbon resistors. Okay, so that's why we use resistance box. If somebody was supposed to ask, so I was expecting the question, sir, why do we use resistance box only in our class, in our labs, right? I was expecting this question. So resistance box is used because it doesn't give lots of error, whereas a carbon resistors or any resistor will give a significant amount of error. Okay. Now what happens? Yeah, when I connected this key, so plug key is there. So there is this plug key. I'll connect this key. What happens? There will be some amount of current I flowing through this. Now, yeah. Now, what do we see here? We have an upper arm. So this is, so when the current flows here, then it will be flowing through this upper arm, and there is this wire. I'll call this one as upper arm and the wire as lower arm. Now, what happens inside a galvanometer? So, okay, inside this meter bridge. So a meter bridge has a galvanometer connected from the midpoint, say connected from B, point B, and it is connected to the galvanometer, and the other end of the galvanometer is connected to a jockey. So don't say jockey. Okay, it's jockey. Okay, jockey. So what is jockey? So it will be something more like a pen. Okay, so it will be a steel pen. I can say it's a steel pen. So it will be having a pointed edge and a screw type of thing here, and it will be having a screw to tie here. A wire will pass from here, and it is connected to galvanometer, one end of the galvanometer. So what type of errors, what is the disadvantage of it? So when we are doing an experiment, Priyanka, so one of your friends is asking, sir, why should we not use that carbon resistor? So if we use that carbon resistor, there will be some error. So when we are doing experiment, we don't want much of errors. So this is an experiment actually, guys. Meter bridge is an experiment. We don't want errors in an experiment. So if we use the color coded resistors, there will be 5% and 10% error, right? So when in our calculations also we should consider that error. So when we are calculating S, we have to consider that error also. That way, the value of unknown resistance will also contain some error. So to avoid that error, we neglect that. I mean, we don't use the carbon resistors. Okay, got it? Please give the confirmation if you have got. Why do we not use carbon resistors? Okay, that's different. So we have jockey. Now what is happening? So one end of this galvanometer is connected to jockey, and I'll start sliding this jockey from one end of the meter scale. Say I have a meter scale marked from 0 to 100 centimeters. Okay, so I'll start from left, say 0 to a certain value. So yeah, I'll try to slide this jockey over this wire. Okay, sir, if we change length, then resistance changes. So how we find correct length to find exact resistance? So yes, Harika, so we are not going to change. Okay, I will come there, Harika, we'll come there. Please wait. So what we are considering, that's the reason we are considering this wire. So as I said before, this wire will be having a fixed value of resistance. It does not vary with temperature. Okay. Now let's come to study how it works. So the wire of meter bridge is made up of a material whose resistance remains constant and does not vary with temperature. Now, first thing what we do, so we'll connect our circuit as shown in the figure. So we'll do this experiment. Okay. So we have connected our resistance unknown value. So this is our unknown value we have connected. And from the standard resistance box, I'll write resistance box as RB. We have removed a known value of resistance. Okay, this is known standard value. Now, what I'll do, I'll take this jockey which is connected to the galvanometer. So since there exists a current, so there exists a potential difference, right? So there exists a potential difference between the upper arm and lower arm of the meter bridge. So since there exists a potential difference, So there will be a higher potential at this upper arm. There will be some lower potential at this lower arm. Maybe because of this length. Okay. Now what I'll do? What I'll do? As I move along the length of the conductor, the resistance of the current flowing through this wire also, or the current flowing through the galvanometer also varies. As I move along the wire, the potential varies and the galvanometer current also varies. So the jockey is slided over the 1 meter wire till a point. It reaches that there is zero deflection in the galvanometer. What I'll do, I'll start from one end and try to slide over this wire. Okay, I'll try to slide over this wire until I get zero deflection in the galvanometer. Once I get zero deflection, I'll call that point. So I'll mark this point. Say, suppose I got zero deflection at this point. I'll call this point as N. Okay, this point N is nothing but the null point. So what is null point, guys, now? What do you think null point is? So there exists a point where on sliding through the wire, so I'll get a point where my galvanometer current or the current flowing from this point B to point B becomes zero. Okay, that is called as my null point. So what is this null point? So this null point is nothing but the balanced condition. So this is similar to that of a Wheatstone's bridge balance condition. So yeah, there will be no deflections in the galvanometer. So this point is called as null point, and there will be no current flowing through this galvanometer. Now this null point, what to do? So if we provide, so we know the length of this conductor from 0 to this point N. So let us call it as L. If this length is L, and this length, since we know this is 100 centimeter wire, so this is a 100 centimeter wire, the remaining length is 100 minus L centimeters, right? Now, if we get the values of resistivity, so if we know the value of rho, if you know the value of A, and if we know the value of L, can we find the resistance of this wire? Guys, please reply. Can we find the resistance of the wire? Yes. Okay, ma'am. Cool. So yeah, if we are given with R, okay, if we are given with resistivity, area and length, we can find the resistance of the wire. The resistance of the wire is R is equal to rho L upon A, right? Yes, we can find. So we got the resistance of wire AD and DC. Okay. Now once we get this, what should we do? So at the null point, the meter bridge behaves as a balanced Wheatstone bridge. So since this behaves as a balanced Wheatstone bridge, we can write the equations of balanced Wheatstone bridge. So what we can write? We can write that, yeah, R by resistance AD. So there is a resistance AD. Since this is the length of the wire from A to D, I have one resistance. I'll call it resistance RAD. From D to Z, I have another resistance of the wire. I'll call it RDC. Now, what is the value of RAD? What is the value of RAD? RAD will be equals to, I know the value of rho. Yes, correct, Priyanka. Rho, I know the value of length L upon A. Similarly, what is the value of RDC? RDC will be rho 100 minus L upon A. So here, what I'm going to use is, I'll call this length L as L1 and the length 100 minus L as L2. Okay, guys, please make this, please note this. I'm going to call length L as L1 and the remaining length, that is 100 minus L, as L2. Okay, now on substituting, we get, so what do we get? On substituting, we get R by rho L1 by A equals to S by rho L2 by A. So where rho is the resistivity, A is area of cross section, L1 is the length L, L2 is length 100 minus L. Okay. Now what can we cancel out from this equation? What can we cancel out? Yes, we can cancel out rho, values of rho and values of A on both sides. Then the expression becomes R by L1 is equal to S by L2. Rearranging it to find the value of R, the unknown value of resistance is given by R is equals to S times of L1 by L2. Here we don't need the value of rho or A. We just need the value of length of the conductor. As here, L1 is L and L2 is 100 minus L. So this is how we are going to find the value of an unknown resistance of the conductor connected between the points A and B in a Wheatstone bridge or in a meter bridge. So meter bridge is the practical application of Wheatstone's bridge. Okay, guys. So I hope everyone have understood this. Any doubts in this, guys? Please give confirmation. I hope everyone have understood this. Guys, if you have any doubts, please ask me. Feel free to ask all doubts, guys. Come on. Hope everyone have understood this. I'm waiting for a reply, guys. Please reply. Okay. ನಾನು ಮೌನಂ ಸಮ್ಮತ ಲಕ್ಷಣಂ ಅಂತ ತಗೊಳಕ್ಕಾಗಲ್ಲ. Please ಹೇಳಿ. Okay. Okay, cool. Next over, we'll go to next. So I have a question for you guys. In the given figure, so please try to solve this question. So in the given figure, for the zero deflection in a galvanometer of meter bridge, so for in this given figure, there exists a zero deflection for galvanometer, and for the given length. Please try to find that length. Okay. So there is R1, that is 15 ohm, R2 is equal to 10 ohm, A is existing here, AB and BC. Please try to find out. Can you find out the length? Please take 1 minute of time to solve this and please let me know. So I'll launch the MCQ for you guys. Please try to solve this. Sir, in one doubt, in Wheatstone bridge, if galvanometer deflects, how we can find unknown resistance? What are the consequences? So that's the reason, Hariprasad. So galvanometer should not deflect. Okay, we should find the balancing point. So until then, we have to slide our job key. Okay, so in a properly connected Wheatstone bridge, there will be a null point for sure. There will be a 100%. There will be a null point if you have connected all the circuit elements properly. Okay, it should anyway satisfy this condition. So meter bridge works on the principle of ratio of resistances. Okay, meter bridge compares the ratios of resistance. So there should be a null point for sure. Okay, guys, I'm launching an MCQ. Please answer in this. Okay. Hope everyone have solved this. Solve Manidra. Guys, did you solve? I'm waiting for the answer. Okay, Krishmodi, correct answer. Namrata, correct answer. Supama. Others, guys, come on, try to answer. Okay, pause. Radhika, correct answer. Very good. Others, guys, come on. Hari Prasad, correct answer. Okay, guys, come on, let's check that. So, okay, let's check the answer. I'm going to end the code. So, most of you had given me option B as the answer. So, yes, option B is the correct answer. So, let's check how it works, how it's happening. So, the length AB, we know that length AB is length L. Let us consider length AB is equals to L. And length BC will be 100 minus L. So, for zero deflection galvanometer, so we know that R1 by RAB will be equals to R2 by RBC. So ulta tagonಡ್ರು ಏನು ಬೇಜಾರಿಲ್ಲ. We studied it as R1 by RAB equals to R2 by RBC. Okay. So yeah, whatever it should be ratio. So going this way, 15 upon L should be equals to 10 upon 100 minus L. Okay. Please try to solve this. So you'll get 1500. 10L cross multiplying, you'll get 10L is equals to 100 minus L into 15, that is 25L is equals to 1500. So from here, L is equals to 1500 divided by 25. This is 60. Okay. So L is equals to 60 centimeters. This is the answer. Yes, guys, got it? Cool. So yeah, next we come to the principle of potentiometer. Okay. So what is a potentiometer, guys? What is a potentiometer? So what do you know about potentiometer? So a potentiometer is a device. So let us study about the working principle of potentiometer for that. So we use potentiometer to find the compare two cells, or to compare the internal resistance, or to find out the internal resistance of a battery. Okay. So the potentiometer, so working principle of potentiometer is given as, so the potentiometer works on the principle that when a constant current flows through a wire, so when we have a constant amount of current, say if I have some wire, okay, let me draw a uniform wire. Okay. So if I have some wire, and if there is some constant amount of current, so I'll connect a battery to this. I'll connect a battery to this, and I have a resistance such that, okay, I'll connect the resistance, variable resistance. Okay. So yeah, let me consider a wire of length, say 4 times of L. So in meter bridge, we had considered L is equals to 100 meters, right? In meter bridge, we had considered length of the wire is 100 centimeters. Here, we'll be considering its 4 times, okay? 4L, that is 4 meter wire. So in potentiometer, we'll be considering a 4 meter wire. So each 4 meter wire is connected with a strip, a connecting strip, okay? Conducting strip. Now what's happening? What's the working principle of potentiometer? So the potentiometer works on the principle that when a constant amount of current flows through the wire, say I is the current flowing through this wire, through a uniform cross-section area. So if this wire has a uniform cross-sectional area, then the potential drop between these 2 points, say I have 2 points A and B, the potential drop between these 2 points is yeah, the potential drop between these 2 points is directly proportional to the length of the wire. Okay, so the potential drop E or V, the potential drop. So if E is the EMF connected and V is the potential drop. Potential drop and what is potential drop? So there will be some amount of potential which is dropping across the resistors, right? Across any conductor. So that is your potential drop. For the given amount of resistance, there will be some potential, a constant potential across these 2 ends of the conductor. That is called as the potential drop. So this potential drop is directly proportional to the length of this conductor. So this potential drop is equated by a constant called as a potential gradient. Phi is called as the potential gradient. Now what is potential gradient? Guys, I hope this is known to you. Do you guys know what is a potential gradient? Hi. So do you know what is a potential gradient? Yes. Super. So potential gradient now is given as phi. So it's given by phi. Yes. It's phi is now using this equation. I can write phi as V upon L, or this also can be written as dV upon dr. Okay, dV upon dr. Okay. But yes, exactly. Rashmani. Super. So it's nothing but the potential per unit length. Potential per unit length. So potential gradient is nothing but the potential per unit length. Say if I know some length, now using this potential gradient, yes, it is defined as potential per unit length. Correct. Super awesome. So potential gradient is nothing but potential per unit length. Now if we know the value of potential gradient, can we find out the potential at any point in this 4-meter wire? Right? So my potential gradient, or the value of potential at point A, will be very high, and as we go along with the wire, as we go along the length of the wire, what happens to the potential, guys? So at point A, we have the highest potential. Now as we go along the wire, length of the wire, what happens to the potential? One word answer, please. Yes, super Prajwal. Awesome, very good. Yes, as we go along the length of the wire, super Namrata, very good. So as we go along the length of the wire, the potential decreases. So there exists a potential gradient between points A and B. There exists a potential gradient between points A and B, from higher potential to lower potential. As we go along the length of the wire, the potential decreases. Okay, the potential drop. Okay, so there exists a potential drop V. So the potential gradient is potential drop per unit length, or potential per unit length. Okay, so this is the basic construction of a potentiometer. So a potentiometer will be consisting of, so guys, please follow this. A potentiometer is consisting of an external battery EMF E connected in series with an external resistance R. So this resistance, external resistance, is a rheostat. So rheostat is a variable resistor. This variable resistor is fixed such a way. Okay, this is a variable resistor, but it's fixed to a value. Okay, this rheostat is fixed to a known value. Okay, so whenever there exists a current, exists a current, there is some potential drop across this conductor. Since there is some potential drop across this conductor, what should exist in the conductor? So guys, there is some potential drop across conductor, right? So what should exist in the conductor? So there exists some resistance, right? There should be some resistance in the conductor. That is the reason we are having some potential drop. So I'll call this resistance as R1. So okay, this also will be having, okay, this also will be having a key, okay, plug key. So guys, I hope most of you know this. If we have a plug key like this, is it opened or closed? If we have a plug key like this, is it open or closed? Okay, this is open, okay, open circuit. So if we have plug key like this with a dot, it is closed. Okay, remember. So now I don't have any potential drop. When I connect this plug key, there will be some potential drop across this. Okay, and there exists some resistance. This is the basic construction of a potentiometer. A potentiometer will consist of the EMF E, external EMF E, and an external variable resistance which is fixed at a value. So we can call this a fixed resistance 2. So it's external resistance R connected with a key plug key K, and it's connected with a 4-meter long wire. Okay, 4-meter long uniform cross section wire. Okay, so now when I have connected this, so when I have connected this wire along with this EMF E, there exists a current, right? What is the value of this current now? Guys, can we calculate what is the value of current in this circuit? What is the value of current I? So apply Ohm's law, guys. So we can see that this resistance of the wire R1 is in series with this external resistance R. So we can write by using Ohm's law, I is equals to E by R plus R1. Okay. Yes, I is equals to VE divided by R plus R1. Please remember this equation. So this is required later. Now, if you observe the circuit, okay, now if you observe the circuit, there exists potential gradient Vy and there exists potential drop V1. So now phi we denoted as Vr phi is equals to V by L. Now for this potential, for this 4-meter wire, what is the potential gradient? Can you say for this 4-meter wire, what is the potential gradient? Phi will be equals to, yes, the potential across the 4-meter wire Vr1 upon the length of that wire L, right? So if you want to find out the potential gradient, so what is Vr1 guys here? What is this Vr1? So if this is the potential across this wire AB, what is the value of this potential Vr1? Then Vr1 is equals to what? From here. Shall we redraw this? I think we have to. I'll try to redraw this. We have a battery with variable resistance connected across the feed and this. Point P. So this is it. Point A to point P. We have the resistance is R1. The potential drop across is VR1. This is the external EMF E. External resistance R. So what is this VR1 given by? Again, from Ohm's law, VR1 is nothing but I into R1. Okay, VR1 is nothing but I into R1. Now, on substituting the values of VR1, we will get phi is equals to, what is phi, guys? Phi is IR1 upon L. Okay. Now, if we substitute the value of I, which we calculated in previous slide, that is I is equals to E by R plus R1. Sir, why are you doing this? How many have this doubt? Why am I doing this? So this is the general expression. So I just wanted to give you a brief idea of how potential gradient is, or what potential gradient is, and what are different ways to write potential gradient. So if I substitute this value of I here, so we get I is so on substituting the value of I, substituting I, we get there is some lag between my laptop and my writing. So phi will be equals to E upon R plus R1. So I wrote the value of I into R1 divided by L. So if I try to reorder, so E R1 upon R plus R1 into L. So this is the equation, right? Here the value of E R1 R is constant. Only variable is L. So this is called as, this is the potential gradient of this 4-meter long wire, guys. So this is the potential gradient of this 4-meter long wire. Did you get this? This is a basic construction of potentiometer. Now let us study about the application of potentiometer. So before we go to application part, please let me know you have understood about the potential gradient. Any doubts in potential gradient or derivation of potential gradient for this 4-meter long wire? ಏನಾದ್ರು ಡೌಟ್ ಇದೆಯಾ potential gradient ಮತ್ತೆ potential gradient of 4-meter long wire ಅಲ್ಲಿ ಏನಾದ್ರು ಡೌಟ್ ಇದೆಯಾ? Any doubts in that, guys? Please give confirmation if there is no doubt. We move on. Okay, here. Cool, guys. So now let us let us start with the application of potentiometer. So first application of potentiometer is comparison of two cells. So let us consider, let us see the circuit, how it is. So here again, since we have considered E everywhere, let us also consider E. Okay. So yes, this is the X and this is resistances R1. Okay. Now for this construction, what do we have? We have the same potentiometer, but this potentiometer is now connected with a three-way switch. So this is a three-way switch. So why is it called three-way switch? So what we can do, so whenever we want to compare any one of the cells, so we can just short circuit this two. So we can short circuit points 1 and 3 so that we get the value of epsilon 1. And if you want to calculate the value of epsilon 2, we can short circuit the value, switch position 2 and 3. Okay. So yeah, this is the construction of your potentiometer. Yes, Chetan. Chetan, you raised the hand. Any doubts? Please ask. Chetan, I'm waiting for you. If you have any doubts, please ask. Okay, I consider you raised by mistake. Cool. So if you have any doubts, please ask. Okay. Okay. So what we did at point A, we connected two EMFs. Okay, to compare. So in this application, what we are going to do, we are going to compare two EMF cells. So we have two cells, epsilon 1 and epsilon 2. Okay. So let us consider two cells, epsilon 1 and epsilon 2. So here we have a condition. So this epsilon 1 and epsilon 2 should be strictly less than E. Guys, are you getting this? Now, can someone explain me why is this condition given? Value of epsilon 1 and epsilon 2. Guys, please. I know my handwriting is very poor, I guess. Can you make out my handwriting? Okay, I'll try to write clearly. Of epsilon 1 and epsilon 2 should be strictly less than E. For comparison. Why? So for comparison of two batteries, the value of my epsilon 1 and epsilon 2 should be less than E. Why? Who is going to answer this? Please note this. This is very, very necessary condition. Why do we need this condition? Waiting for answer. Yeah, if even yes, exactly, Krishnori. Cool, super. Suppose what happens if epsilon 1 and epsilon 2 are greater than E? Just imagine. So observe the circuit, guys. If epsilon 1 and epsilon 2 are less than E, then the current will flow from the capital E, the main battery EMF, the external EMF which is connected from here, and the difference in these EMFs. So the difference between E and epsilon 1, epsilon 2, these are compared in this potentiometer setup, guys. Always this external battery EMF is compared with the additional EMFs. So so test cells, we can call them as test cells. So the test cells EMF is always compared with the main battery EMF. Okay. Suppose if the test cells have more energy or more voltage than that of the EMF connected, then there is a possibility that the current will flow in the opposite direction and there won't be a deflection in galvanometer. Okay. If this is not satisfied, so else I'll give the else condition also. Else what will happen? There will be current in reverse direction. Then no deflection in galvanometer. Okay. So then there will be no deflection in galvanometer. There will be current in reverse direction and no deflections in galvanometer. If epsilon 1 and epsilon 2 are greater than E, then there will be a reverse current and no deflection, and there will be no deflection in galvanometer. So to avoid that, we are giving this condition in very first thing. What is the condition we have? The epsilon 1 and epsilon 2, the batteries, the test cells, should not be greater than the external EMF connected for this experiment. Compare two cells, the value of epsilon 1 and epsilon 2 should not be greater than EMF E. Otherwise, there will be no deflections, and there will be current in reverse direction. So, yeah, what we are going to do first? So first step is step 1. What we are going to do? Let's connect switch 1 and 3. So let's connect 1 and 3. What happens now? Okay, guys. In first case, I connected 1 and 3. What will happen now? Come on, tell me. Yes, I connected switch 1 and 3. So what will happen? There exists some current I, and there exists some current say there exists some current from this EMF 2. Okay, so there will be, so because of this current and this current, there will be difference in potentials. There will exist a potential gradient between the points A and point C. Here points A and point C. Okay, initially consider point B, right? So let us still consider it as point B only. So between points A and B, there exists a potential gradient, and so when this EMF is connected, so E1 is connected now, right? So there exists a potential drop between this. So we can find a null point. So like N1. So on connecting 1 and 3, we get there exists some potential gradient, and there is a null point N1. So on sliding the jockey of the galvanometer, we'll find the first null point N1. Okay. So what's all happening? Current flows. A potential gradient is set up, right? A potential gradient is set up. So third thing, we are on sliding jockey. On sliding jockey, we find null point N1. Okay, we find null point N1. So this is the null point. Say we slide it all the way from here. We found our first null point. So now what can we write? So N1 is the null point of potential E1. What can we write now? N1 is the null point of potential gradient. N1 is the null point of EMF E1. So can we write the potential gradient? Okay, so this was my first case. In second case, what I'll do? Okay, we'll write together. Okay, so in second case, if we connect the switches 2 and 3, so similarly on connecting, I will write this in a different color. Guys, please let me know if my handwriting is not proper, or if you are not making out. 2 and 3. What will happen? So current flows, a potential gradient is set up. Okay. And null point N2. So in second case, we'll get the null point N2. Yes, fine. So now what we are going to do, guys? Yeah, we found the null point N1 and we found the null point N2. Now I want to find what is the potential gradient. At midpoint, the EMF from cell will be equal. So at this null point, what is happening? From this point, the EMFs of the external battery and the EMF of this test cells will be equal at the null point. What's happening at the null point? So I'll write that also. At null point, EMF from E and epsilon will be equal. That is why we are going to get a null point. So when we have same potential, there will be no flow of current. So the EMF, due to EMF E, and because of this E, okay, because of this E, there will be a null point at N1 because of E and E1, epsilon 1. Why? At this point N1, what does this null point say? This null point says that at point N1, the potential due to external EMF and the potential due to the test cell will be equal. So there will be no current. Okay. Now potential gradients. So epsilon 1 will be given as 5 times of L1. So my null point N1 is found at this length of L1. And my null point L2 will be found at a length L2. Then if L1 and L2 are the respective lengths of potential gradients, of null points N1 and N2, then epsilon 1 will be equals to 5 times of L1. We will call this equation 1. Similarly, epsilon 2 ಏನಾಗುತ್ತೆ? What will happen to epsilon 2? Guys, come on, tell me what is epsilon 2? Anyone reply please. What is my epsilon 2 then in terms of potential gradient? Yes, 5 times of, right? So I'll call this equation 2. Now taking their ratios. So let us take their ratios. We get what? So equation 1 divided by equation 2, do it. What will we get? So epsilon 1 by epsilon 2 is equals to 5L1 upon 5L2. From here, my potential gradients 5 and 5 gets cancelled. So we don't have to calculate the potential gradient at this step at all. So potential gradient again. So we can write epsilon 1 upon epsilon 2, the test cells EMF epsilon 1 upon epsilon 2 equals to L1 upon L2. Using this equation, we can find out, okay, we can find out the EMFs of any unknown value. Okay, we can find the value of unknown EMF of any test cell. Okay, let's take an example. Okay, so this is the expression used to find the EMF of unknown value. So guys, I hope everyone have got this. So what are we going to do? I'll just summarize quickly. So we consider this potentiometer. Now I have two EMFs, epsilon 1 and epsilon 2, and I have a three-way switch. So this three-way switch has capacity to connect any one of the EMF at one time, only one. So we will be connecting one EMF test cell at one time and comparing with the external EMF. So this is a three-way switch. So this is three-way switch. Okay. So the value of EMF. Okay, don't confuse. So this is the very strict condition given. The value of test cells epsilon 1 and epsilon 2 should be strictly less than the value of E. Otherwise, we won't get the reflections. So first, let us connect 1 and 3. What happens? The current flows and a potential drop is set up, and a potential gradient is also set up. On sliding the jockey from the initial point to the point through the length. So from here, if we start to slide the jockey, what happens? The jockey will get a null point. The current through galvanometer will be 0 at one point. That point we call it as null point N1. Okay, at length L1. Okay, so this is the null point N1 at length L1. Similarly, now we'll connect the switch positions, change the switch positions from 1, 3 to 2, 3. So on connecting 2 and 3, a potential gradient is set up and null point L2 is found at, okay, where is it found? At L2. Okay, it's found at L2. Now, at null point, so what is this null point? So null point is nothing but the EMF of my external EMF and the test cell will be equal at that point. So that is the null point. So if we try to write the expressions for the potential gradient or EMFs using the initial equation which we studied for potentiometer, so we get epsilon 1 is equals to 5 times of L1, where 5 is our potential gradient. We will consider this as equation 1. Similarly, for equation 2, so for EMF tester 2, epsilon 2 will be equals to 5 times of L2. So that is equation 2. Now, taking the ratios, we get equation 1 divided by equation 2, 5 and epsilon 1 by epsilon 2 equals to 5L1 by 5L2. From here, pi cancels, potential gradient values cancels. So the change in EMF or the ratios of EMF is directly or is equals to the lengths of the respective null points. Okay. From this, we can find value of unknown self potential using this equation. So suppose if you know the value of epsilon 1 and epsilon 1, say if I call it epsilon 1 as 1.5 volts, say I am using a small AA size battery. AA size battery, I hope everyone has seen. So this 1.5 volts battery. So suppose I have a 1.5 volts battery. Okay. Then yeah, in potentiometer, I found its length L1 is equals to 60 centimeters. So I have another EMF, I have another battery. Okay, positive, negative. I don't know what is this EMF, epsilon 2. I don't know what is it. So I'm using the potentiometer. I found the length L1 as 60 centimeter, and null point for E2 was L2 is equals to 360 centimeters. Okay. Can you find E2? What is my value of E2? Come on, let's try to do this. So my value of E1 or epsilon 1 is 1.5 volts. Length 1 is 60 centimeters. Null point 1 is at the length 60 centimeters. Null point 2 is at the length of 360 centimeters. What is the value of my epsilon 2? Or the value of my cell 2? Cell 2 value enta heli. Hope everyone is doing. Yes, correct, Madhavi. Hari Prasad, check your answer. Priyanka, correct. Others, guys. Ramakrishna Reddy, correct. Oh my God. Namrata, correct. Anusha, check your answer. Namrata, very good. Anusha, check my answer. Please check your answer. So here, others, please try to give. Hari Prasad, check your answer again and give the right answer. Rakesh, correct answer. Super. Super. Awesome. So guys, let's check this. Okay. So what we have, we want to find epsilon 2. So let's rearrange this. Okay. Yes, correct, Hari Prasad. Super. So if we keep epsilon 2 on one side and rearrange, we get epsilon 2 is equals to epsilon 1 into L2 upon L1. So substitute the values and find the answer. So that is 1.5 into 360 upon 60. Okay. Super Pradwal, correct answer. So 6 were 36. 6 into 1.5 is 2. 6 into 1.5, yes, 9. So my value of E2 will be 9 volts. Okay. Value of E2 is 9 volts. Cool, guys. Hope everyone have understood how we compare the value of two cells. and how to find the value of an unknown EMF. So if we ever get an EMF, so if we want to find that EMF, so suppose if we don't have any, if you want to find accurate value, so where are we going to use this method, guys? Sir, why are we going to use this, sir? So why are we going to use this method when we have a voltmeter? We can connect a voltmeter to the battery. We'll get the exact value. Why should we need this? I'm expecting that question. Yeah, calculate it. Why no one is asking that question? So guys, this method, what will happen? So this method will give us an accurate value. Okay. So accurate and precise value. Though in today's world we have accurate and precision tools, say such as the voltmeter also can measure up to, say if you have a very good quality voltmeter, it can measure, yeah, it can measure up to the microvolts level. Okay, a very good value multimeter. It will cost a bit, but it will measure your value. It will give your value up to precision of or resolution of microvolts, say 9.000056. So that much amount of volts it can measure. Suppose if you are using very low value of voltages, say if you have used a multimeter or voltmeter ever, so whatever the multimeter or voltmeter you have used in your schools will be of 0 to 5 volts only. Suppose if you have very less value, very small valued voltmeter, then you can't measure the lowest value, least value of voltages. So in those cases, this potentiometer comes handy to calculate that very small values of EMFs. That's why they are going to use that. Okay. So that was one application. Sir, I am unable to see this thing. Yeah, come up. Please check your internet connection. Guys, is the screen visible? Guys, is the screen visible, guys? Please let me know. Guys, is my screen visible? Please reply. Yes. Okay, thank you. Okay, so let's come to the second part. So comparison of two cells. We are done with that. So let's come to the second part. Say the internal resistance. To find the internal resistance of cells. Say suppose we have a cell and we have to find the internal resistance of that cell. So the circuit setup looks similar. But instead of that, what we will be having is we'll be having, instead of one cell, or sorry, instead of two cells connected, we'll be connecting only one cell. Okay, one test cell. In the other arm, we'll be connecting a switch and a resistance box. Okay, that's the only difference. So to find the internal resistance of a cell, what we are going to do, we are going to use the same. We are going to use the same terminologies everywhere. Please note that this is E, this is V. Okay. Cool. So instead of connecting two cells, I have connected only one cell, and the other arm is connected with a switch and a resistance box. Okay, this is the only change. Otherwise, there is no change. Okay, so to find the internal resistance of the cell, we connected a resistance box with switch. Here, manana, instead of two cells. So when key is open, so initially key will be open. So first case, key is open. So when my key is open, now I'll slide my galvanometer. I'll slide my jog key. What value will I get? So first case, my key is open. Okay. So this circuit shows where is the key is closed. But let us assume the first case, the key is open. So what will happen now when key is open? Key open is ಏನಾಗುತ್ತೆ? So yes, there exists some current I. So there will be some potential gradient set up. So here also current flows in the circuit, flows through wire. There exists a potential gradient exists, potential drop exists. So since potential gradient and potential drop exists, there is current through the galvanometer. So at a length L, sorry, we'll still consider at length L1, we find null point N1. Okay. So similar to previous case, here in first case the key is open, the key K2. Okay. Let me be specific. The key K2 is open. K2 open irutte, the key K2 is open. Now we'll find the null point. So we got the null point as N1 at length L1. Okay. So what is the potential gradient expression or EMF expression? We can write EMF expression E is equals to epsilon is equals to 5 times of L1. So let's keep it equation. Keep this equation as equation 1. Okay. Now in second case. So let's come to the second case. So I'll write second case here. So second case on closing switch key. Closing key K2. So when I close this key K2, what happens? So again, guys, wow, super Hari Prasad, Santosh Aito. Okay, I'm closing key K2. What happens, guys? Come on. So on closing key K2, there exists the current flows through the wire. So second thing, there exists a potential gradient exists. So and potential drop exists, V exists, potential drop. So here the potential drop is across what? Resistance box. So there exists a potential drop across the resistance box. So now again, null point, we get a null point. So fourth thing, we get null point N2 at length L2. So what is the equation we get? So we know that here I don't have an EMF. Guys, please observe, we don't have an EMF here, but there exists a potential drop V across this. So there exists a potential drop V across this circuit. If, guys, come on, tell me, if there is a potential drop V across this resistor box, what is the potential drop across this EMF V? So, and suppose if we had an internal resistance, okay, let me represent that internal resistance with a different color. Suppose if there exists an internal resistance R, then the same amount of potential which is existing across the resistance box, same amount of potential will also exist across the internal resistance of the battery. Can I say this? Yes. Yes, no, you're not ready. See what's happening? Since I don't have any power here, any EMF source here, but all the power is absorbed either from this battery or from this battery. Okay. Now there exists a potential drop across this resistance. Hold on. From this point A, and let's find this point as P. From this point A to this point P, there exists a potential drop V. Hold on. The same amount of potential drop can also be existing on R if the current through galvanometer is 0. E condition is how many did not understand this? Hope everyone got this. See, when my galvanometer current is 0, I'll find a null point N2. If I say the galvanometer current is 0, then I can also say that the current in these two circuits, so the current flowing in these two circuits, I should be also equal, or the potential drop, okay, the potential drop across this internal resistance and this resistance box should be same. That potential drop is given by V. Okay. This V, now if we try to write the potential gradient form, V is equals to 5 times of L2. Okay, this is equation number 2. So in the order artha agidya, I hope everyone have understood till here. So this is one point where most people get confusion. So good that you guys understood. Now, yeah, I'm going to rewrite both the equations. So we got equation 1, epsilon is equals to 5 times of L1 and V is equals to 5 times of L2. Okay, this is my second equation. So guys, now if you see here, there exists a common current I. Why? Since my current through IG, current to galvanometer, if current to galvanometer is going to be 0, there exists a current I. How much is the value of this potential V? How can I write the value of V? Can I write it as the current I flowing through the resistance box R using Ohm's law? Can we write V as V is equals to I into R, where R is the resistance from resistance box? Okay, so I have made, yeah, good. So since current is 0, now dividing, so we'll rewrite this equation as epsilon is equals to 5 times of L1. Then instead of V, I'm going to substitute into what I'll get, IR is equals to 5 times of L2. So guys, these steps are very, very important. Please listen. Now to find the internal resistance. So please listen very carefully. To find internal resistance. Okay, so we are going to do one approximation. So one thing. So the current in circuit is given by. So if you observe this circuit, so the current in this circuit is I. Hold on. So if the current in this circuit is I, so there is some current in this direction, right? The current in this circuit is I. Hold on. So what is the value of this current I? If you consider this loop, where I is the current flowing in this direction, what is the value of this I? This is the very, very crucial point of this derivation. You don't know one there and one more. If you get this, you got this equation, you got this derivation. So in this loop, what is the value of I? So apply Ohm's law, guys. I is equals to V, the common potential. This is a parallel circuit. If you observe, this is a parallel circuit. So I mean, the potential remains the same. And if I consider this as a loop, then the current will also remain the same. Sorry, young sorry, this don't confuse with my predecessor. So there exists a common potential V, and the current flowing through this. Okay, let us now consider V. If I consider, okay, let us consider this loop only. So if I is the current in this loop, then apply Ohm's law and find what is my current I. So from here, I will be equal to epsilon times epsilon upon resistance of this resistor R. Okay, I have heard this also R. I can ಇದು R, ಎರಡು R ಆಗುತ್ತೆ. So that this one was R1. Let me call this as R dash. R dash. So this resistance is R dash. R dash times, so R dash plus R. Can I write this by applying Ohm's law in this loop? E is equals to I into R dash plus R ಅಂತ ಬರೆದು using this loop I can write E is equals to I into R dash plus R, or I is equals to epsilon upon R dash plus R. Can I write this equation? So this is the point where I'm stressing, guys. Please note this. We have considered a small loop here. In this loop, the current remains the same when my galvanometer current is zero. Note that when my galvanometer current is zero, there exists a current inside this loop. So whatever the amount of current enters this point, same amount of current also goes back. Since my galvanometer current is zero, I is zero, no current comes here. All the current which is coming from here is going back here. Are you getting this? So by applying Ohm's law to this loop, I get I is equal to E by epsilon by R plus R dash. Please give confirmation, guys. This is the only question point. Constant. If you get this system. Please give confirmation, guys. Come on. Or if you have doubts, please ask me, sir. What I'm repeating again. Say at this point, when I close this plug key 2 and I slided the galvanometer, so I slided the jockey, I found a null point N2. There will, at this null point N2, there is no current flowing through the galvanometer. This means in this closed loop, whatever the amount of current entering this point, this node P, the amount of current entering this node P is also same amount of current which is leaving P in the opposite direction. So nothing is going to the galvanometer since I is zero. So every current which is entering here is also going back in the loop. So if I apply Ohm's law here, I'll get I is equal to E by R dash plus R. Yes. Here. Okay, cool. Here. Okay. So now I'm substituting that value. So we got I is equals to epsilon upon R dash plus R. So let me consider R dash that. So substituting this value here. Substituting here, we get, yes, what do we get? Epsilon is equals to pi L1 and epsilon upon R dash plus R equals to pi L2. So this is my new equation A and equation B. Okay. Now what we are going to do? Guys, are you following? Okay. Divide A by B. So you'll get this epsilon is equal to epsilon upon epsilon by R dash plus R, okay, into R1, right? Into R dash is equals to L1. What did I do? Phi is equals to L1 by L2. So my phi cancels from here. I have the ratio. Okay, we start that down. So this is the end, guys. This is the last concept of your chapter. So from here again, epsilon and epsilon cancels. So remaining we get R dash plus R upon R dash is equals to L1 upon L2. Rearranging this. Solving for R, we get, so 1 plus R upon R dash is equals to L1 upon L2, or R is equals to, so what is the value of R, guys? Small r is equals to R dash times L1 upon L2 minus 1. So this is the final expression we get for the value of internal, to find the value of internal resistance of an EMF. Okay, so small r is equals to R dash times of L1 upon L2 minus 1. Okay, guys, yes, I hope everyone is listening. So this was the application of potentiometer, and this completes your chapter current electricity. So there is one more part, RC networks, guys. There is one more part called as RC networks. So RC networks mean I don't know if you have it in your syllabus. So anyway, tomorrow we'll be studying RC networks. So tomorrow's class we'll be studying about RC networks. So guys, please reply in chat box. So have you ever studied about charging and discharging of RC circuits? So a capacitor, whenever we are going to connect a capacitor, always we should connect a resistor in series with that. So that is important. So why, if we don't connect a resistor, what will happen to that capacitor? Or how will it react in the circuit? Then, so can we construct some delay circuits? So how do you know how traffic signals work? Traffic signal ಹೇಗೆ work ಆಗುತ್ತೆ? So can you construct a traffic light, red, yellow, and green using RC networks? Yes, ma. Actually, I have some questions on this. So yes, I have some questions on this, but I don't have time to discuss now. So we'll put these questions in tomorrow's beginning part of the class. So I'll give more questions. Actually, yeah, guys, did you have any class yesterday? One more thing. Did you have any class yesterday? No, this was I don't know. I was on week off. Okay, you had biology. Cool. Super, guys. Then okay, you had biology and maths also, right? Was maths also there? I think there was supposed to be math also. I don't know if biology is happening. Biology. Okay, never mind. So in next week, I think we'll be having physics on physics and chemistry classes. Okay. Well, guys, any doubt in today's class? If you have any doubts, we'll learn that. Please feel free to share the doubts. So in tomorrow's class, we'll first try to finish the problems. So I'll give some introductory. I'll give these problems some standard questions. So if you solve those 2-3 questions, that's enough. Okay. If you solve those 2-3 questions, similar type of questions will be asked in your JEE mains also. Hope everyone have started your preparation for JEE mains, guys. Sorry, 100%. Nice. Okay, so I hope everyone have started your preparation for your JEE mains. Please start preparation if you have not yet started, and try to finish at least 50% plus of your syllabus. So your GATE application, sorry, GATE is for me. Your JEE mains applications would be sometime available, maybe by end of this month or by next month beginning. I mean next year beginning, next month beginning. Okay. So anyway, we'll keep you guys updated. Okay, guys. Then. So neat idea, Neat. I think best person to discuss neat is your biology teacher, or I'll try to find out figure out information. Okay, so I'll get that. Neat. I think you are having neat only one time, right? In that year, not here. So okay, guys. Then we'll meet again on tomorrow's class. Please complete the NPS, and if you have any doubts, please stay back. Else we can drop off. Thank you. Bye bye. Guys, please, if you have any doubts, please ask. Please call and you could ask. If you don't have doubts, you could drop off. Please give the NPS and you could drop off. Okay, guys. Then yeah. Okay, it's time 4:30. I have to end the meet. So we'll meet again.